Hello. So today we're going to be talking about the inverse problem of the form D equals GM, where D is your data, G is your forward model or model in general, and M are your model parameter guesses. And for this tutorial, we're just going to focus on intuition, so I'm going to drop that vector notation. So the point of this video is to help you get intuition from how to start here and get to the Newton's method, Gauss-Newton, or quasi-Newton methods. And first thing you have to think about is how do we linearize? So when we say linearize, we're talking about linearizing around your model parameter guesses. So we can say that our next guess is our current guess plus some small perturbation. And just as a side note, you might see this written with an alpha. And this is just basically a scaling of how much we trust the search direction, but we're going to ignore that for this video. So, rewriting our model in terms of our next guess, we can write that our next guess is the same thing as your current guess plus some perturbation. And right now your brain should be flashing, saying that we can use Taylor's expansion. So that's the same thing as GMK plus the gradient at MK times that small perturbation, and then collecting all those higher order terms, which we're actually just going to ignore. So from here, we want to take the gradient, and as always, set it equal to 0. Okay, so when you do this, you'll find the following form. And rearranging that for your small perturbation, you can find that it's equal to the second derivative times inverse times the first derivative. Okay, so that's one of our main ingredients. Next, we're going to kind of move beyond this type of thinking and just think about the fact that we want to solve a least squares solution. We want to find a least squares solution. And basically that means that we're going to write our misfit as just the magnitude of the residual squared, which our residuals is just the difference between our data and what our model predicts. So another way to write this in vector form is just 1/2 R transpose R. So our second main ingredient is taking the gradient of the misfit. So we find that it's the same thing as this. But what is this? Well, looking at this, you'll be able to see that the derivative of the residuals with respect to M is the same thing as the negative derivative of your model over del M. And you'll know that to just be the Jacobian, which I denote with a J. So you can really write this and then rearranging in the order, which you can prove to yourself is necessary, as this. Okay, so that's first main ingredient, or second one. The only other ingredient that you need is taking the derivative of this as well, or the second derivative of your misfit. So when you do that, using the product rule, you'll find the following. Which I'll replace this with a J again. And then, looking at this, which is our solution for how we should update the model, we just plug in what we just found. So we know that the second derivative is this, so inverse, and then we know that the first derivative is this. So this is actually pretty much everything you need to know intuitive-wise about how to get to Newton's method. And something cool is that quasi-Newton is just getting rid of this term, and then Gauss-Newton is getting rid of all higher order or second order information. So this one is Gauss-Newton. Yeah, so hopefully this helped build intuition of where this equation comes from.